Bismillah ar-Rahman ar-Rahim. Pressure. First of all, introduction of force. The unit of force is Newton, which gives an object of 1 kilogram and acceleration of 1 meter per second. The force of gravity, as we can see, equals 9.81 meter per second. This is on any object. So if this object is 1 kilogram, we can say that 1 kilogram object equals 9.81 Newton. So whenever I figure out the correlation between a kilogram and Newton, I will find that 1 Newton equals 102 gram weight. So we are shifting from Newton to gram weight. The units of pressure, we have of course the systemic international system, which considers Pascal as the unit of pressure. The interrelationship between pressure and force is given in the following example. So first of all, we have the two syringe. One of them is the 2 millimeter and the other one is the 20 millimeter. So whenever I want to figure out the surface, doubling the diameter, increase the surface by 4 times. So this is the diameter of the both each syringe whenever I shift it to meter instead of centimeter. So each of them, if they are being used, giving a force of 25 Newton, suppose each syringe will of course yield the pressure. The one on the upper one, the 2 millimeter, will give a pressure of around 500 kilopascal, and the other one will give a pressure of 100 kilopascal, and the systolic blood pressure is 16 kilopascal. So these two high pressure can make accidents during the process of local intravenous anesthesia. Of course, we must consider this high pressure whenever I use syringe pump and infusion pump. The second thing regarding the correlation is the expiratory valve. Of course, we have this expiratory valve, we recap, and we have a spring acting on an area of the diaphragm. Of course, this area is balanced by the pressure upwards and downwards. We need only 50 Pascal to open this valve whenever the patient is under normal spontaneous respiration. The second thing is the reducing valve. This reducing valve, of course, controls the flow and the pressure of oxygen. We have a high pressure source and a low pressure source. So suppose the low pressure source, which is coming from the syringe, is decreased, the spring acting on the diaphragm, upper diaphragm, will descend the rod downwards, opening the opening, making the opening more wide, so that the oxygen will flow more to the low pressure compartment, maintaining the pressure. This reducing valve, we call it one stage reducing valve. The second stage reducing valve, it's another component attached to that one, where there is a large diaphragm and a tilting rod. This system is created during the negative respiration of the patient, which activates the system so that the oxygen can be relieved. So this is used as a demand valve. These are the some example, in addition to, of course, the warning device that may be attached in the old anesthetic apparatus, where whistling occurs whenever the pressure is increased. It's based on, of course, the one we mentioned before. And then after that, we have the gauge and the absolute pressure. The gauge pressure and absolute pressure. The gauge pressure is the pressure on the manometer. So if we have a full cylinder of oxygen, 10 millimeters, we'll find that the gauge will read 137 bar whenever it's fully full. So whenever it's completely empty, you expect that the gauge, the pressure inside this cylinder will be 0. No, it's not 0. It's 1 atmosphere. So the absolute pressure is the gauge pressure, which is on the dial plus 1 atmosphere. Pressure in liquids, of course, liquids with a height exerts a pressure, you see. So if we have two manometers, one is filled with saline at a level of 10.2 centimeter, and the other one also is filled but this one has a surface area of 1 square centimeter, and the other one has a surface area of 4 square centimeter, so it's 4 times. So what's the end result of the pressure yielded by this liquid on the downward tube? It will reach 1 kilopascal whenever I change the non-orthodox to the orthodox method. What was the meaning of that? Of course, this 10.2 centimeter of water equals 10.2 gram of water. So the centimeters of water equals, suppose, this figure of grams. Of course, as we know, 102 gram weight equals 1 Newton. So from this figure we can figure out that we have a pressure and we have an area. We can figure out the force. So the end result of both, the diameter of the tube will not affect much the end result of the pressure yield by this height of the tube. You see. Now we come to what we call the effect of surface tension. Surface tension is the tension on the surface, you see. So suppose we have, as we can see from the figure, molecules of the liquid inwards the liquid and on the surface. You can see the line of attraction between the molecules goes in every direction, and the molecules downwards deep in the liquid. Apart from the one on the surface, we can find that there is a different attraction. So this different attraction on the surface create what we call the surface tension. It makes tangential lines on the surface. This tangential line stretches the water. Suppose the water droplets whenever I throw, making it as if it is skin, stretches as a skin. So this is what we call the surface tension, you see. Now we come to the importance of having capillary tubes. These capillary tubes has what we call the meniscus. Meniscus means that there are forces that makes the height of the level of the manometer increases upwards, because there are forces between the molecules from each other as the surface tension. Also the molecules of the liquid and the glass containers. So this pulls the level upwards. This is regarding saline. According to what we will see now, that we can find difficulty to estimate the height of this manometer. On the other hand, if we use mercury, we can find that the height is makes instead of a concave, it makes a convex. Why? Because mercury, regarding of course the surface tension between molecules, it does not is not much affected by the forces of the manometer. So this is why, or we call it, does not wet the tube. You see, effect of slope of the manometer. Of course, when we incline the manometer, we can visualize much better height of the difference of applied pressure. Mercury manometers, of course, we have mercury. Mercury has a density which is 13.6 more than water. So if whenever I want to shift from millimeter mercury to centimeter water, I must multiply by 13.6. It has been shown on these two manometers, where when I apply 1 kilopascal, it will increase only the height of the water to 10.2 centimeters, whereas the mercury manometer will increase only 7.5 millimeter. On the other hand, 1 kilopascal elevates, of course, as we can see, the mercury manometer to 260 millimeter mercury. Of course, this manometer is different from that, but it has a closed ended. This is what we call it a device to measure barometer, to measure the atmospheric pressure. It's not. It gives a real pressure of the atmospheric pressure. This we call it absolute pressure. Most of the pressure we use in ventilators and blood pressure and so forth are called gauge pressure. Now we come to what we call differential pressure. Differential pressure is the pressure. Suppose we have a capsule, as you can see from the diagram, and we apply both pressure on different sides. So this is what we call the differential pressure. It will yield a pressure regarding both pressures. The methods to measure high pressure, of course, all these pressures are used to measure minimal pressure. Of course, we cannot not use mercury manometer to estimate the pressure in the cylinders, because it's very, very high pressure. So instead, we have to what we call the boarding gauge method to measure the high pressure, where we have a hollow tube. This hollow tube, whenever it's been applied on it high pressure, it will straighten and will activate a pointer over scale. This will yield the pressure. On the other hand, of course, this we call it Android. This we have, I'm sorry, the other one is the Android method to measure blood pressure, which is made of a capsule. This capsule, whenever I apply pressure, as you can see, for this is of course is absolute, because it's a closed compartment. This is a gauge because it's attached to atmospheric pressure. So whenever I apply pressure, this capsule is compressed and will activate also a pointer on a scale by a gear system. Of course, this is what we call the differential pressure. The pressure upwards of this barometer, which measures the atmospheric pressure, we call it torr. Torr means 1 torr equals 1 millimeter mercury. Of course, we have another units to measure the blood pressure. I'm sorry, the pressure part of the kilopascal. In America, we use a pound. So 14.5 pounds per inch square equals 1 bar. So whenever the syringe, the cylinder is full, we find it is around 2,000 pressure, atmospheric pressure. So this is the hint about the subject. I hope that I didn't exceed 15 minutes. This is my aim of this lecture. So thank you very much.